In 1990, a team of scientists isolated a highly unstable atomic particle in a lab. Unstable particles like this naturally decay and change states, but when the researchers aimed their equipment to measure it, the particles stopped. It froze, completely, hovering in midair. The team hadn't introduced a force field. They didn't alter the temperature, drop a physical barrier, or touch the atom in any way. All they did was watch it. We've all heard the old proverb that a watched pot never boils. In human psychology, it's just a trick of impatience. But at the quantum level, this proverb turns out to be literal physics. Physicists call it the quantum Zeno effect. In our everyday lives, we assume that the physical world keeps turning whether we pay attention to it or not. The world we see every day feels solid, clear, and completely fixed in place. But this experiment forces us to ask a deeply uncomfortable question. How can the passive, seemingly harmless act of simply looking at a piece of matter act as a physical brake pedal on its existence? To understand how observation stalls time, we must shrink down. When you zoom past the predictable rules of heavy objects and enter the atomic scale, matter stops acting like hard billiard balls. It becomes a blurry, undefined fog of probability. An electron doesn't exist in one specific spot. It exists in a cloud of maybe. The most famous proof of this weirdness is the double slit experiment. The premise is simple. Fire a single particle toward a solid wall that has two vertical gaps or slits cut into it. If you let the particle fly without tracking its exact path, it defies common sense. It acts like a ripple of water, passing through both slits simultaneously, crashing into its own waves and leaving a complex, multi-striped interference pattern on the wall behind it. A single particle physically collides with itself. But here is the twist. If you place a detector at the slits just to track which specific hole the particle goes through, literally just watching it, that complex wave pattern instantly vanishes. The particle behaves like a normal, solid bullet, passing through one slit and leaving a basic two-stripe pattern. You didn't touch it, you just watched it. Physicists call this the observer effect. The mere act of measuring a particle forces its blurry cloud of possibilities to collapse into a single concrete reality. Now, let's apply that rule back to our frozen atom from 1990. For an unstable particle to decay from one state to another, it requires a tiny window of time. This decay process isn't instant, it is a slow buildup. As the particle prepares to change, it gradually shifts away from being a solid point and becomes that blurry, undefined state of transition again. But remember what observation does. Every single time a scientist takes a measurement during this transition, the observer effect forces that blurry cloud to collapse right back into its original, undecayed state. The researchers realized that if they fired their measurement lasers at incredibly high speeds, the particle was constantly forced back to square one. Observe, reset. Observe, reset. Time appears frozen in the lab because rapid observation acts as a relentless reset button. The atom never gets the uninterrupted time it needs to actually complete its change. This leaves us with a deeply unsettling question. If matter only takes a solid, defined shape when it is being measured, does reality actually exist when no one is looking? To software engineers, this behavior sounds suspiciously familiar. In a video game engine, the computer doesn't generate the entire digital world at once. To save processing power, distant mountains and dark alleys remain unrendered until the exact moment the player looks at them. If our universe is aggressively saving processing power in a similar way, it would need to have a maximum resolution. In physics, there is an absolute limit to how small space can be divided, called the Planck length. At 1.6 times 10 to the power of negative 35 meters, it is essentially the smallest possible pixel size of our universe. In the 2010s, researchers at Fermilab built a massive machine called the holometer. Their goal was to zoom past the atomic scale and hunt for a tiny jitter, seeing if reality is made of flickering pixels. At its bleeding edge, modern physics is actively testing the boundary where the physical universe behaves identically to a digital grid. This naturally leads to Nick Bostrom's simulation theory. He argues that if a highly advanced civilization could create one perfectly simulated universe, they could easily create billions. Statistically, that makes the odds of us living in the one true original reality extremely low. But we have to look at the hard data. The Fermilab holometer ran its tests and found absolutely zero evidence of spacetime pixels or jitter. There is no proof that we are trapped in a giant computer. We also need to be clear about what an observer actually is. It doesn't require human consciousness. A mechanical sensor taking a reading or a random stray atom colliding counts as a measurement that collapses the wave of probability. Yet even without a literal computer running a simulation, the math holds up. The physical world relies on data. Information and observation appear to be foundational building blocks of the universe, standing right alongside matter and energy as the very things that make existence possible. Those scientists in 1990 didn't glitch the universe. By forcing that atom to repeatedly freeze, they caught matter in its purest, unrendered state. For a brief moment, they were simply looking at reality's source code.